All right, we just figured out that before the equivalence point, after adding 30 milliliters of our titrant, our pH is equal to 5.36. Our next problem is to say what is the pH at the equivalence point. And so what we need to do is again work through one of these sheets, this is part C, asking who's there, what's the chemistry that happens, how to incorporate volume changes, using an equilibrium or ice table to think about who's left in solution and their concentrations, and from that determine pH. As we'll see here, we're not going to be able to use the Henderson-Hasselbalch equation when we're at or beyond the equivalence point. All right, so thinking about all the players that we have in solution. So at this point, we always treat each of these titrations as though we start right from the beginning. So HPR, 0.1 molar, 40 milliliters, and so that is 0.004 moles. We've got sodium hydroxide, which generates sodium ions in solution, which we're not worried about, and hydroxide ions. Hydroxide ions are 0.1 molar. Again, we've got 40 milliliters, which is 0.004 moles. Chemistry that happens, same as the chemistry that happened with our earlier step. HPR, when it encounters a molecule of our titrant OH-, will have a proton stripped away to generate water, and then the conjugate base. We use an ICF table to keep track of the moles. So we've got 0.004 moles of HPR, 0.004 moles of OH-. We're not concerned about water, and we have no conjugate base initially. Since these numbers are equal, these are each limiting reactants, such that when we complete this table, we're left with none of the titrant and none of our starting weak acid. However, what is important is the fact that we have an equivalent number of moles of PR- that are generated at the equivalence point. The volume change that we need to consider is the fact that we started with 40 milliliters in our flask. We've delivered 40 milliliters from our burette, so we have 80 milliliters total. And we'll need to use that to figure out the concentration of PR- that we have at equilibrium. So the new concentration we have of PR- is going to be equal to 0.004 moles in 80 milliliters, which is 0.08 liters. And so we have 0.05 molar. You'll notice if we want to think about the concentration of HPR that we have, it's 0. And the concentration of OH- that we have, that is 0 at the equivalence point. So there's really only one molecule at the equivalence point that we're going to need to think about something happening with. So at the equivalence point, if the only thing that we have is PR-, the only equilibria that we can draw is PR- encountering a molecule of water and generating HPR and leaving behind hydroxide. But one of the things that we'll have to make sure to realize is if we've written this equation like this, we need to use a Kb value. So Kb, again, is going to be equal to Kw divided by Ka. The Ka value for this chemistry was 1.3 times 10 to the minus fifth. So if we calculate the Kb value, Kb is going to be equal to 7.69 times 10 to the minus 10th. We propagate our ice table just like we did in all of our previous problems. We start with 0.05 molar PR-. Water is not part of our equilibrium expression. Consider 0 contributions from other sources for HPR and OH-. We're going to lose some of this and gain some of these. 0.05 minus X, X and X. Again, thinking about a pre-check that we have here, even though we have a small amount here, a very small equilibrium constant is going to be such that our pre-check will be fine. So Kb, again, is equal to concentration of HPR times OH- times the concentration of PR-, so that's X. I'm going to incorporate my assumption, 0.05 propagate this to solve for x. Remember that x is equal to our hydroxide concentration. That's equal to 6.20 times 10 to the minus 6 molar. Negative log of 6.20 times 10 to the minus 6 is going to equal POH, which is 5.21. 14 minus that number gives us a pH of 8.79. So, and this should make sense. If we have a weak acid and a strong base, the pH at the equivalence point should be greater than 7. That's just a qualitative thing to remember. Also, I want to point out here that the Henderson-Hasselbalch equation is not an option here. If we think about what we have in solution once we've finished our chemistry, the only thing that we have in solution is PR minus. Since we don't have the weak acid, we only have the conjugate base. We cannot use the Henderson-Hasselbalch equation. So mapping this in again onto our cheat sheet here, if we are at the equivalence point of a weak acid, strong base titration, we use an ice table in KB to determine the hydroxide concentration when we have A minus protonated by water. We didn't really specifically say, but we did use an ICF table to kind of figure out the number of moles of the conjugate base that we made. Okay, use the new volume to kind of figure out what the concentration of that guy was, and then importantly, used an ice table, and then we had to use the KB value because that was the equilibrium that was available to us. Because we used KB, our X is equal to OH minus, so we needed to then use one more kind of manipulation to convert POH into pH for this solution. So, and as we can see by our graph here, here's pH 7. The pH of an equivalence point of a weak acid strong base titration will always be greater than 7. Okay, so that was part C. Moving on to part D. Right? So part C, the pH was 8.79. Part D, we're after the equivalence point. We've added an additional 10 milliliters beyond this, so a total of 50 milliliters of titrant. What I'm going to show you with this problem is actually going to be a lot more than you actually need to do. So I'll show you at the end kind of, well, what are the real parts that you need to do kind of when you're going through this calculation. But I want to show you all steps of it to kind of convince you why we can make a simplifying shortcut. All right, part D. So let's think about who's in solution. Remembering, each time we look at these titrations, we're considering it as though it started from the beginning. So HPR, 0.1 molar, 40 milliliters, means we've got 0.004 moles. We've got OH minus, well, we really had sodium, which we don't concern ourselves with, and OH minus, 0.1 molar. We've got 50 milliliters, which means we've got 0.005 moles. So the chemistry is going to be the same as what we've seen before. So what, again, we're going to see is something that looks very similar to what we just wrote down for part C, except the numbers are going to change a little bit. So we'll point that out as we walk through this. So the chemistry is that HPR, when it encounters an ion of hydroxide, has its proton ripped away to make water and leave behind PR minus. Our ICF table, which allows us to keep track of all of our species, we've got 0.004 moles of HPR, 0.005 moles of OH minus. Water we're not concerned about. We're assuming no additional sources of PR minus. Now the HPR becomes our limiting reactant. When we are at the equivalence point, they were both kind of limiting reactants. And then in part B, when we are before the equivalence point, our stuff in our titrant, the stuff in our burette, was our limiting reagent. So now with our HPR being our limiting reagent, that's how we propagate our change column. And we're ending up with 0 for what was our limiting reactant. we've got some excess hydroxide now floating around in solution, in addition to the conjugate base of our weak acid. So remembering that chemistry and ICF tables give us numbers of moles, we need to use the new volume, which is 40 plus 50 or 90 milliliters, to figure out what the concentration of these species are. So the new concentration of hydroxide is 0.001 divided by 90 milliliters. And that's going to be equal to 0.044 molar. The HPR new concentration, we've got none of that left. So that's going to be 0. And then the PR minus concentration is going to be equal to 0.004 over 0.09 liters. And that's equal to 0.011 molar. And as I'm going to show you as we walk through a little bit of an ice table, this guy is really going to be insignificant when compared to that guy. So as I'm going to show you that, I'm going to convince you of that in the sample problem, but what I want to make sure that you understand is this is really the only guy that's going to dictate pH in solution at this point. So let's walk through an ice table so that we can prove that to ourselves. So the ice table that's available for this guy, PR minus, if it finds a water molecule, we'll grab a proton and leave behind hydroxide. So PR minus is 0.044. All right, so now we've got our right numbers in our ice table here. Propagate our x's through. Remembering we're going to be using KB here, and KB is equal to 7.69 times 10 to the minus 10th. And so our assumptions are going to be valid here. So KB is going to be equal to x, 0.011, 0.044. What we can see here is when we propagate and solve for x, our x is going to be quite small, 3.076 times 10 to the minus 9th. That's a very small number for the concentration of hydroxide that's going to be contributed by PR minus finding a water molecule. Very small, very insignificant compared to the 0.011 molar that we have here. So again, we commented that this was insignificant when compared to this value. So we can write an equilibrium to talk about it, but in reality, we will be able to omit this. I just kind of had it here to show you why we're able to omit it, but you don't need to think about the equilibrium for the conjugate base that's left in solution, because the concentration of hydroxide is really going to be dominated by the excess titrant that we have. Okay, so really we just need to consider the fact that the OH minus new concentration from the excess titrant is really what's going to dictate the pH of our solution. And again, that 0.011 molar. If we take the negative log of this OH minus concentration, that's going to equal POH, which equals 1.9586. 14 minus that gives us our pH, which is 12.04. So if we look at our cheat sheet again, after the equivalence point, we do need to use an ice table, right? Using an ice table allowed us to figure out the moles of OH minus that we have in excess. Once we figured out the number of moles of OH minus in excess, we needed to divide by the total volume of solution to get the concentration of OH minus in excess. And then we could take negative log of that to give us POH, and then 14 minus that to give us pH. So quite a lengthy problem for our weak-strong combination. So giving us 12.04 at the end here. Looking at the pH before the titration starts, before the equivalence point, at the equivalence point for a weak acid strong base is always going to be greater than 7. And then after the equivalence point, where the pH is dominated by the excess amount of titrant that we have. And again, the titrant that we have here is OH minus.